The second major piece of data that Bohr was trying to use in his model was Rutherford's discovery of the nucleus. This came in 1911. Rutherford's experiment consisted of an alpha particle beam aimed at a foil made of gold. And it was already thought that gold was, the atoms were much smaller than the spacing between them, and so that they would expect most of these alpha particles to pass right through. But the surprising discovery was that in many cases these alpha particles were sometimes scattered backwards. And we know from first-year physics, anytime something very big and heavy recoils back in the same direction from which it came, it means that it encountered something much heavier. So this means that something inside the atom was, in fact, very dense and very immovable. So Rutherford was trying to explain some earlier data from his students, Geiger and Marsden. In Rutherford's model, the atom had some sort of dense charge from a nucleus, and this would be something that could deflect the alpha particle, leaving the nucleus of the atom essentially unchanged in position because of its larger size. The different scattering angles in Rutherford's model could be thought of as arising from alpha particles, which came into different levels of grazing incidence with the nucleus. So if one defines a so-called impact parameter, distance b, which is the distance of closest approach to that nucleus, something where b steadily approaches 0 is a case where the alpha particle would turn around and head right back in its original direction. Something where that parameter b is relatively large would leave the alpha particle heading off in the same direction as it originally came in. And we can see why different impact parameters would cause different amounts of scattering angle, because the electric field of this nucleus would repel this alpha particle by different amounts, because the force would go as 1 over that b squared. And I won't go through the full derivation of this, but I will just point out that Rutherford's interpretation correctly pointed out that the atom had something that was very heavy at its core, the gold nucleus, and this nucleus had a like charge to the alpha particle, namely positive. It's this repulsion from the nucleus that caused the varying scattering angles of the alphas. With 2020 hindsight, we can say that actually it would have required the discovery of radioactivity and high energy alpha particles to ever make this discovery. The original data from Geiger and Marsden used alpha particles that had about a kinetic energy of 6 MeV. And these alpha particles had a wavelength that was sufficiently small that could resolve the small size of the nucleus. Today we know the nucleus has a radius on the order of 1 to 10 femtometers. And so in order to be able to resolve such a small size, one needs to have a probe whose wavelength is comparable to that size, or else the nucleus, the features of the nucleus are blurred out by diffraction, much the same way as we use an electron microscope to see the very smallest features, the surface of a material, because otherwise visible light would be limited by diffraction. So I'd like you to take a moment and calculate what is the wavelength of such an alpha particle, and determine why it is that it was important that we had such a high energy source of alphas in order to see the nucleus of the atom. I'll try to go through that solution now. It's worth remembering that the mass of the alpha particle is about 4 times the mass of the proton. Consequently, this kinetic energy is quite a bit smaller than the mass energy of the alpha particle, and we may use the approximation that the alpha particle is non-relativistic. In other words, its kinetic energy is just p squared over 2m. I'm going to rewrite this by multiplying and dividing by a factor of c squared. And in this way, I can obtain that the momentum times c of the alpha particle is the square root of 2 times its mass energy times its kinetic energy, where this is about 4 proton masses, or 4 GeV, and this is about 6 MeV. In rough terms, this comes out to be about 220 MeV. And since momentum is h over lambda, then in this case, lambda is hc over pc. Which is 1240 MeV femtometers divided by 220 MeV, which is about 3 femtometers. Oh, excuse me, 6 femtometers. So this discovery was rather critical because it told us that the nucleus was quite small, and we wouldn't have seen it until previous to this because only probes using visible light would have had wavelengths in the order of nanometers.